Hello and thank you for attending this session at the GT Global Conference. I am Joseph Solomon. I work at GT as a technical pre-sales engineer out of our Detroit area office, focusing in the areas of electrification. Today I'll be talking about my master's work that I did at the University of Michigan using GT Autolion, investigating our new in version 2021 electrochemical and mechanical modeling capabilities, specifically looking at the performance of a lithium-ion battery cell and comparing it with experimental data. Let's start with a quick overview of GT Autolion's capabilities and why we need to do this in the first place. So, lithium-ion batteries continue to grow in market share, whether that's in the EV market or consumer electronics or so on. And as that need increases, the need for higher energy density and new materials becomes more and more apparent, whether that's silicon anodes or lithium metal anodes or solid state electrolytes. These all will have an important factor to play as we increase energy density, range, and so on in these products. As these new products or materials come online, they do have larger changes in volume during charge and discharge cycles, which has a drastic effect on cell design and packaging design for whether it's a battery pack or the cell itself. It's important to consider the links between all of these different physical domains to get the most out of your cell in development, understanding design trade-offs, and making more informed decisions, whether it's for your vehicle, your cell phone, or your medical device, as an example. And GT Autolion is specifically uniquely positioned to answer this problem, whether it's in the mechanical domain, which we'll be focusing on today, the thermal domain with our detailed thermal capabilities, degradation with our physics-based models, and as well electrochemical modeling as well. These can all be tied together in one model in one platform. The basis of the electrochemical model in GT Autolion is the Newman-Doyle-Fuller pseudo-2D model. And what that is able to capture is as follows. Charge transfer kinetics as lithium moves during charge and discharge throughout the cell. The lithium diffusion throughout the electrolyte, the cathode, separator, and anode are discretized linearly into parts as shown in the image on the right. Within each of those discretizations through the electrolyte is a solid representation for the active material, as shown here, discretized radially. And then finally, charge conservation is observed as Ohm's law throughout each of the discretizations. Now let's discuss what is occurring within the active material during charge and discharge, specifically under lithiation. As shown in these three images, the state of lithiation or charge affects the size of the active material, shown in gray in these boxes here, depending on the amount of lithium available within the cell. At smaller or fully delithiated portions, the cell has higher porosity compared to a fully lithiated state with lower porosity. Now this does have an effect on stress and strain. So the answer to this question is yes, and we will be diving into this next. In version 2021 of GT Autolion, mechanical models are fully integrated into the tool. So as lithium moves during charge and discharge and active material swells, as shown in the image here, with boundary conditions being applied at both sides of the cathode and anode, the strain or change in volume is able to be taken into account with these new mechanical models, as well as the change in porosity. How does this mechanical model integration in GT Autolion help you from a practical standpoint within the tool? One first example, which is what we'll be looking at today, is how stress and strain affects cell performance. Another is seeing how